Hello everyone, my name is Mike and you're watching Polymath Unlimited. In this series we are building a Logisim simulation of an 8-bit CPU with the following design goals in mind. First, the CPU should be simple enough to make a physical build practical. Second, the CPU should be capable of complex operations. And third, the CPU should be easy to program. In the last video, we learned how to build logic gates from transistors, which will enable us to build a physical version of our CPU once design work is completed. In this video, we will discuss binary numbers and design some circuits that we will be able to use to make our CPU perform addition operations on those numbers. This is an important step forward because addition forms the basis of many essential tasks that computers do. In a computer, numbers are represented in binary, which simply means there are only two digits we can use, 1 and 0. This actually isn't as confusing as it sounds at first, though. Binary numbers work just like the normal numbers we are used to. For example, when you count from 1 to 10, once you hit 9, you are out of numbers to use, so you simply put a 1 in the next place and start over at 0 in the ones place to make 10. In binary, digits are called bits, and we simply run out of digits faster. So if we start counting in binary, as soon as we reach 1, we are already out of digits to use, so we simply put a 1 in the next place and start over with 0 in the ones place to make 2. The difference is that in binary, instead of the places being powers of 10, the places are instead powers of 2. So instead of the ones, tens, hundreds, and thousands places, we have the ones place, twos place, fours place, eights place, 16s place, and so on. For example, the binary number 1011 is a 4-bit number that has a 1 in the 8s place, 2s place, and 1s place, making the number 8 plus 2 plus 1, which is 11. Because binary numbers work the same as any other number, we can apply the same addition rules to binary numbers as we would to normal numbers. For example, to perform the operation 5 plus 9 equals 14, we simply take 0101 and add 1001. In the first column, 1 plus 1 equals 2, but 2 in binary is 10, so we carry the 1 to the next column. Next, 1 plus 0 equals 1. Then 1 plus 0 equals 1, and finally 0 plus 1 equals 1. So our final result is 1110, which is the correct binary form of 14. Now that we know how binary addition works, we can build a circuit called an adder. We will start by building what is known as a half adder, which takes two 1-bit numbers and adds them together. Before we start putting down logic gates, let's build a truth table for our circuit. This is simply a table that lists all possible combinations of input values and what the outputs should be for those inputs. We want our half adder to take two inputs, A and B. This means we will have 4 possible input combinations. We will have 2 outputs called out and carry out. If we go through all of our possible input combinations, we find that 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 0 and carry 1. If we look at the truth table we made, we can see that out should be 1 if either of the inputs but not both are 1, and carry out should be 1 only if both of the inputs are 1. This means that if we use an XOR gate, that should generate our out signal, and if we use an AND gate, that should generate our carry out signal. This simple circuit works well for single-bit numbers. However, if we want to do addition on larger numbers, we need to build a full adder. This is simply 2 half adders with the output of the first adder feeding into the second. We connect a carry in input to the other input of the second half adder, and we take the carry outs of both half adders and feed them into an OR gate, and use the output of that OR gate as the carry out of the full adder. We can chain multiple full adders together by taking the carry out of each full adder and feeding it into the carry in of the next one. Since we are building an 8-bit computer, here is an example of an 8-bit adder which chains 8 full adders together in order to add two 8-bit numbers. To show how you can actually build one of these circuits, I built a transistor version using the NMOS design principles we discussed in the last video. I have replaced the XOR gates with XNOR gates, and I have also replaced all the other gates with NOR gates. This implements the same logic as we discussed above, but it is easier to build because it uses fewer transistors. Here is that same circuit on a breadboard. I also built 3 more so I could make a 4-bit adder. Here you can see it performing the same 5 plus 9 equals 14 calculation as in the example from before. With this adder, we have a solid foundation on which to build more complex circuits that can do more operations than just addition, bringing us one step closer to our goal of creating a fully functional CPU. In the next video, we will talk about how we can use binary to represent negative numbers, which will allow us to do subtraction. Until then, feel free to play around in Logisim or maybe grab some transistors and see what you can create. Thank you for watching, and I will see you next time.